Doing work in home is really tough task for us. We will be losing our energy so easily. When we were so younger at the time, we will not be having much work to do. So we love to help our mom in cooking. We always love to do whatever she is asking us to do. Either it's the baking work or it is going to be any of the other work, we will love to do those works. But at the same time, when we are growing up, we do have some other works also to do. So this kind of work, when is being asked by someone, we will say them that either we are busy or you're not supposed to get work from me, right? For example, if your mom is asking you to bring a cup of water, your answer will be I'm busy, or you're near to the cup, you can itself bring the water, right? So what is the reason for that is, as we are growing up, what is the work we have to do every day is also getting increasing. As like in this case of the motorcycle over here, it's having a high potential energy. When it's going to go down, the amount of energy of the bike associated with the bike is going to get reduced. So in the starting, the energy what we have is going to be very plenty in amount, and as it keeps on going, the amount of energy is going to get reduced over here. If you are trying to take another example for this, we would have been seeing the weightlifting. So before lifting the weight, you will be having more amount of energy with your body. So when the time is going to continuously increase, after lifting the weight, you will be losing all your energy to lift that weight. So obviously you will be losing energy after you have done this whole process, right? Similarly, when I started doing work in the morning, after a good sleep and had a nutritious breakfast in the morning, if I'm going to start my work, it will be a fresh startup after a rest and a good food. So I'll be having a very huge amount of energy. Let us take that as 1000 joules of energy. I'll be so refreshed so that I'll be doing the work so happily in the morning. When the time is going to keep on going, continuously I'm going to lose my energy. Finally, when it's going to be some hours later, I'll be totally losing most of my energy, which will make me to feel tired. Why all these things are happening? There must be a reason behind it, right? So that's the same thing what we'll be exploring with today's session. Chapter 6: Work, Energy and Power. Subtopics: kinetic energy, work done by a variable force, work energy theorem for a variable force, concept of potential energy. Work done by a constant force. You can see a car over here which is moving with the constant velocity. That means that what is the force which makes this car to be in motion is of constant in magnitude. The gear at which the car travels is going to be of the same magnitude throughout the travel. So whenever we say work done by a constant force, that shows those motion in which we have the constant movement, that is the acceleration of the object becomes zero. When it comes for the practical situation, most of the time it's not possible for us to have the constant force. For example, you can see this car over here again, that the car is on a highway. There is no traffic over here. there is no other cars also going to be nearby this car, so that you can see the car is moving with the constant amount of velocity, so no acceleration. But is that is applicable to the normal situation what we have? If it is going to be a highway also, we will have the other cars, so we may need to take a break when we are going to catch up with another car. So we have to take a break, or we have to turn. So whenever you are going to supply a brake, the speed of that reduces, or whenever you are going to take a turn, then the direction of the car changes. Either the change in the speed or change in the direction will lead us to have the acceleration of the car, so that the car no longer is going to be having a constant force on that. It will always have a variable force. We will be adjusting our gears as well as the brakes at times to make the path to be proper, as you're seeing it over here. We may have turns, right? So the work done by a variable force is going to represent an object in motion which is having the force acting on it with the variation in its magnitude. So when we are trying to do about the work done by a variable force, a constant force is rare. It is the variable force which is more commonly encountered in our daily life. Figure is a plot of varying force in one dimension. That means when I'm telling you the figure shows, that represents the plot what we have over here, which is having its position varying from xi to xf. So the amount of force acting on that is continuously varying over here from the value of it on this x-axis as f of x about this position, and it's continuously varying and it's reaching a final position of f of x with a particular value over here, right? So if the displacement what we are taking is going to be the del x, that is from xi to xf the car is going to travel, but what I'm going to do is I'm going to consider a small displacement done by the object which is going to be of del x. If this del x what I have taken is very small, we can take the force f of x approximately constant. That's why we have a slanting line, nearly a straight line over here. Then the work done is nothing but force into displacement, right? So here the work done will be given by f of x into del x, as the force what we have taken here is f of x and the distance is going to be del x. The same way, the del x what I have taken over here for the small path, the same thing, the del x, that is each and every small part traveled by the car I'm going to take, and if I wanted to know what is the overall work done by this object, then I need to find the overall area under this graph, right? So when we are trying to find out the overall area, the individual rectangles what I have, I can find the area of them and I can sum them, which will be giving me the total work done, right? So the total work done is given by summation over xf to xi f of x into del x. Now instead of doing this, the summation is going to represent the overall addition of the force from the initial position xi to the final position xf, right? Then if you are trying to find out the displacement allowed to approach 0, then the number of terms in the sum increase without limit. But here the sum approaches a definite value equal to the area under the graph, then the work done can be found by the integration from the starting limit to ending limit. You can integrate it, that is indirectly you are doing the sum up. So the work done is going to be given by limit of del x to 0, that is del x, we are going to start it from 0, that is xi should start from 0, summation over xf, f of x into del x is equal to integral of xi to xf, f of x into dx. Thus, for varying force, the work done can be expressed as a definite integral of force over displacement. If the force varies, then we need to use calculus to find the work done. Kinetic energy. Energy is the capability of doing work or ability to do work. As you see over here, the cycling can be done only when we are spending energy. Do the pedaling. So the pedal is in movement. As a result of it, we will also be in movement. So in general, kinetic energy is the energy associated with the motion or moving object. So in the cycling case, the cycle is moving. In the ball case, the ball is in movement, that is motion. And here we could able to see that the truck is going to move along with the weight with that, and you can see the swing as well in motion. So all this can be taken as the example for kinetic energy. When it comes for the kinetic energy formula, as per the definition, kinetic energy is the energy possessed due to the motion. If an object is going to be in movement, then it is an obvious factor that it will have a velocity associated with that. It's having a mass, then it will be having a velocity as well. So half times mass times velocity square is going to give us the kinetic energy. The unit of any type of energy is going to be joule, and we know that velocity will be measured in the unit of meter per second, mass is measured in the unit of kilogram. The next type of energy here is potential energy. Potential energy is the energy associated with the position of the object or virtue of the position of the object. Over here you can able to see the escalator, where you will be standing on the escalator and you will be moving. See, when you are on the first step, you won't be feeling that much fear to hold on, but when the height of that is going to increase, obviously you will be holding the side handles so firmly so that you can avoid falling. So whenever the height increases, the amount of gravity pulling you towards the downward will increase. So that height and the mass associated with your body tells you that how much amount of potential energy you are going to have. Over here, the same potential energy we are talking, but the potential energy over here is going to depend on the energy stored in this extensible part, that is the extensible rope what you have over here. That extension is going to store the energy inside it. So the elastic potential energy is the one what we'll be talking in this case. So in general, potential energy is the energy stored inside the material at its rest state. Now we can able to see here an example for the potential energy. How much potential energy is lost by 5 kg of object to kinetic energy due to the decrease in height of that as 4.5 meter. What is conservation of energy? We know that energy neither destroyed nor created. but one form of energy can be converted into another form of energy. So whenever you are at rest, what is the energy your body and the object with you holding is going to be the potential energy. When you are going to be in movement, the energy, that is the potential energy what you hold, will be converted into kinetic energy, because you want to move. For that you need energy. That energy will be given by the potential energy of your body. Now that is going to be converted into kinetic energy. So, and 5 kg of object we are considering over here, it's going to have a decrease in its height as 4.5. Then we need to find the potential energy associated with that. So, the potential energy formula is mgh. Here the A is nothing but g, acceleration due to gravity, which is of 9.8. To round off, we can take that as 10. So 5 times 10 times 4.5 is giving us 225 kilogram meter square per second square, which is nothing but 1 joule. So here the potential energy of the object is going to be 225 joule. The same thing you will be able to see here. As I told you, the potential energy can be converted into kinetic energy, then the kinetic energy can be converted into potential energy as well. So initially it will be at rest, and then when it's going to come get into motion, it will be having a kinetic energy. When it's reaching the maximum position, it will be having potential energy, because at maximum height the object will rest for a second. Then once again when it's going to go down, it will be having the kinetic energy, right? Similar case of when the water is stored inside the dam, at a height it is going to have a potential energy, but when it's going to be opened through the reservoirs and they are going to reach the turbine at the bottom of it, they are going to be in movement. So that the potential energy, the stored water is the potential energy, and when it's going to start flowing, it's going to have a kinetic energy associated with that. Work energy theorem. Let us have an example. As you are seeing over here, when you are going to be in the starting of the step, you will be having more energy, right? But when it's going to be 200 to 300 steps and you are going to get upstairs, that is, you are going to walk towards the upward, then whatever the energy you were holding with your body, you must be spending that energy to reach this height over here, right? So to do this work, traveling this distance, what is the amount of energy you're spending is called as the work, right? So basically work energy theorem is the gain or reduction of energy in the result of work. It may be sometimes gain in energy, sometimes loss in energy. If we want to write it in the equation format, then the work done is going to be given by change in kinetic energy, or change in potential energy also sometimes we will write. If you are going to double the speed of the object, then you need to do 4 times of work. If you are going to walk from the initial to final, then you will lose less amount of energy. If you are going to run, then you will be losing more amount of energy. That's the same thing telling us over here. Also applies to the change in potential energy, because if you are going to be seated in a place, for example, I'm sitting over here, and from the morning till night, if I'm going to sitting over here, I'm not going to move. To be in the same state for a long time also, my body must be spending energy. So what is the change in energy I'm going to have? In the morning I may have 1000 joules of potential energy. In the night I'm going to have only 500 joules, means the amount of work done by myself is equal to 500 joules, right? But as per physics, it will be taken as 0 work done. The reason for that is there is no displacement associated with my body. It applies to a decreasing speed. Reducing the speed of an object or bringing it to a halt is also going to require energy. There also we are doing a work. Example, applying brakes to slow up moving car. Work is done on it, that is the friction force supplied by the brakes, time distance is going to give us the work done on this car now. The equation we have done already. So the net work done is going to be given by the formula delta EK. And the total work done in terms of that change in kinetic energy is nothing but final kinetic energy minus initial kinetic energy. So half times mass is going to be same for the object, only the velocity is going to be varying. So final kinetic energy means half m vf square minus half m vi square. So this is how we can write the work energy theorem in two different formulas. And when it's going to come for the same work energy theorem over here, we can have the formula in the different way as well. The same work energy theorem only we are going to write over here, but it has been written in a bit different way, which is nothing but we know that work done is going to be given by force times displacement. So force times displacement can also be given by change in kinetic energy over here. That means that it tells us that when a net force does work on the object, then the object speeds up or it's going to slow down. For example, a box is at rest on a frictionless tabletop. The force of gravity and the normal force from the table do zero work on the box. The work done is zero, so the box does not gain or lose kinetic energy. That makes sense. It is at rest, right? So there is no loss of energy of that. So when it's going to be doing a positive work done also, work energy theorem is applicable. That is, if you apply a horizontal force on the object, it will speed up in the direction of the force, which means that you have a positive work done. So that the net work done will be given by the change in kinetic energy. In a negative work done, the force what you are supplying, opposite to the direction of that, you will be having the displacement of the object, but still the object is moving, so the change in kinetic energy of that will be giving you the net work done by the object. Now the formula for the work done and energy we can summarize over here. Work done and energy, both of them are nearly same, because what is the work done you can work done and energy, both of them are same, because what is the work we have done, that depends upon how much amount of energy we spend. So work done is equal to amount of energy spent, which we'll be learning in the next slide as work energy theorem. So work done is given by the formula force into displacement into cos theta, or in general we can write that as force into displacement. Then the kinetic energy formula is half mv square and potential energy formula is mgh. When it's going to be the net work done, then the net force into the displacement done by the object. Or another way, according to work energy theorem, work done, the total work done will be equal to change in kinetic energy what we are going to have. Change in kinetic energy is nothing but m final velocity square minus half m initial velocity square. Or if you are trying to talk about the mechanical energy is the addition of kinetic energy and the potential energy, because mechanical energy is the energy due to the movement as well as the position of the object. So kinetic energy and potential energy together will be giving you what is mechanical energy. Then this is the same thing which is applicable in a fluid which is about in a constant motion. According to the Bernoulli's theorem, half m1 v1 square plus mgh1 must be equal to half mv2 square plus mgh2. Then when we are coming for the next term over here, power, the amount of work done by the object. For example, two persons are going to run a game or race. The total distance should be traveled is going to be 100 meters. 100 The first person crossed that 100 meter in 5 seconds. The second person have completed the same 100 meter in 10 seconds. Now, who's having more power? The person traveled in 5 seconds. Because the work done is same for both of them, one have done it with the less time, the other have done it with more time. So who have done with the less time is going to have more power. That means that power is nothing but amount of work done in the given time. Then the work done can be further written as force into displacement. Displacement over time is nothing but velocity. So the power can be given by force into velocity as well.